class, today we are starting with our first chapter in our business calculus book, and that's chapter R. R is for review, so all of the topics in here should be familiar with you. We're just going to be practicing some of them and maybe solidifying some definitions so that you can get strong at these things before we move on to the actual calculus. We're beginning in section R.1, which is graphs and equations. We're going to be practicing a few items here. And every time we start a section, the objectives will be stated at the beginning of the chapter and at the beginning of the notes. You want to make sure that at the end of the video that you go back and use this sort of as a checklist to say, did I understand these three items? This was our goal. And so we want to make sure that we look at those objectives as a checklist of things that we've learned. Today we're going to cover graphing equations, using the graphs as mathematical models and using those models to make predictions, and then we're also going to carry out calculations involving compound interest. Our first question asks us to graph the equation y is equal to negative 3x plus 2. And I have here a t-chart, that's the thing on the left, and then an empty graph on the right. And notice that on my graph I don't have any numbers written, so it's up to you to write in the numbers and make sure that it's to scale the way that you want it to be. In order to graph this number, typically when we have the y isolated, we just pick values for x to plug into this equation. And what I like to do is look at that coefficient of the x and make sure that if there's a coefficient like that's a fraction, that I use numbers that work well with it. But this is negative 3, so that's going to multiply by whatever x values I choose. I'm going to choose 0 in the middle, and 1 and 2, and then negative 1 and negative 2. So as I plug these values in, you would just say y is equal to negative 3 times x plus 2 and then you put that value of 8 right in here. And we're going to continue doing that. Each line in that t-chart is an ordered pair, so we're going to go to negative 2, 8, and put a dot there, negative 1, 5, and put a dot there. And each of these points will be a solution to this equation because they make that equation true. But then each of those solutions ends up being 1 point on the line of our graph. So I'm going to go start at the middle, which is always my favorite place to start, at 0, 2. I'm going to label it as 2. Then we're going to go to 1, negative 1, labeling the numbers as I put them in. This is 2, negative 4, negative 1, and 5. And I don't have room for negative 2 and 8. But those are all those numbers. And then I'm going to do my best to connect them with a straight line. You want to make sure that your line extends to the end of the graphs on both sides, all the way to the top and the bottom, or to the left and the right. And you want to make sure that if you don't go all the way to the end, you can also put arrows to show that the line continues in both directions indefinitely. Now, you can tell that on your lecture notes, we just finished video example 1. Now, there's a question very similar to this. It's titled book example 1. And as we do our questions, there will most of the time be questions side by side. And this book example is a question that's similar to the one that we just did. You should be able to do it based off of what we did in the video. But if you want extra practice, you can do it. If you want to check your understanding, you can do it. If you want to check your work, the answer is in your textbook, and it's in example 1 in this section. So you can do this, and then you can open your textbook and see if your answer matches what they have. Hopefully you find that a good study tool. To do question number 2, we first realize that it's written in a different format. The y isn't isolated. it's not written in slope-intercept form. It's written in standard form. And this standard form, you can plug numbers in to either x or y to be able to find your ordered pairs. But one of the easiest ways I like to approach this is to write the equation and then solve it for y. So we're going to subtract 2x from both sides and then divide everything by 4. So that you end up with it in slope-intercept form. And then for this one, my x has a coefficient of -1/2. And because of that, I'm going to pick even values of x so that they work well with the coefficient so that I still get integer answers. I like to start in the middle with 0. And then I'm going to go up by 2 and down by 2. So doing this gives me numbers that go well into this equation. And when I plug in -4, notice the -1/2 times the -4 gives us +2. And so we end up there. Now you can finish filling in this t-chart, and I'm going to go ahead and do that. And when you're done filling in that t-chart, then you can put those points on the graph. I'm going to go ahead and start in the middle like I like to start. I'm going to go to 0, 3. I'm going to label it 3. But another thing I'm going to say is that, remember, we talked about when it's y isolated, it's going to be in slope-intercept form. My intercept is 3, and my slope is -1/2. So that's another way that we could have graphed this. So I start at the 3, and I go down 1 over 2, and that is going to be the coordinates 2, 2. And then I go down 1 over 2, that's going to be the coordinates 4, 1. And then we could go the other way. We go up 1, back 2. That's going to be the coordinates -2, 4. And then up 1 over 2. That's the coordinates -4, 5. And once again, if you want to continue putting on dots, you can continue in that pattern, doing the slope to do those dots. And you want your line to go from edge to edge. Now if you have your line going from edge to edge, it's going to be assumed that it goes on in both directions, but alternatively you could also do your arrow on both ends to make sure that we know that that line goes on infinitely. Moving on to question number 3, we can recognize that we see a quadratic and not a linear equation. You should remember that because it says x squared and not just x to the power of 1. And so we're going to be drawing a different type of graph. This is where it's important to have at least 5 points because you want to get the vertex plus 2 points on each side to draw a nice curved parabola. And we always draw parabolas when it is a quadratic equation. So we're going to plug in the values 0, 1, and 2 on one side, and then -1 and -2 on the other side. Let's just go ahead and start plugging those in. Remember that if you have a negative replacing an x, you have to put it in parentheses. Now it should be obvious from the numbers that we got that 0, 5 is the vertex of our parabola because that on either side of that the numbers are equal. We're going to go to 1, 4 and -1, 4 and put dots there, and then we go to 2, 1 and -2, 1 and we put our dots there. And if we had more space on our t-chart, we could put more, but that's good enough for now. What we're going to do is try our best to make a curved parabola. You do want to put arrows on both sides of that parabola, otherwise it looks like you just have a line segment or a parabola segment. And you do want to make sure that your graph is labeled. So double check all your graphs up to now. Make sure that you put numbers on them. Otherwise, I don't know where you're putting your lines and your parabolas at. And that is graphing the parabola. There is another example for you to do on your notes. Hopefully those last 3 examples were very easy and were review for you. As we move on to example number 4, this one might look a little bit different. And the difference here is that the x is isolated and this is written in terms of y. So when we're filling out this chart, I'm going to put the values that I'm going to plug in the y values. That's much easier to solve for. And if I put my values here, starting in the middle and then going incrementally on each side, then when I can plug those numbers in for the y, then I can solve for the value of x. So you can see that I filled it out pretty much the same way that we filled out the other charts. It's just plugging in numbers on the y value to solve for the x value instead. And let's go ahead and graph that. Be careful. I'm going to go ahead and put all my x values on the x-axis. And then I'm going to put the y values that I used on the y-axis. And we're going to graph that. -1, -2 would be this dot right here. 2, -1, 3, 0, 2, +1, and -1, +2. This is a little bit different. It's like a sideways facing parabola. Try your best to make it curved at the vertex. It's not a V, it's more of a U shape. And there we go. There's our sideways parabola. And that's our graph of this equation. And make sure you practice this again. Do book example 4. When we're looking at mathematical models, we recognize them as word problems. But the reason that we're using the verbiage mathematical models is because these are models of everyday life using math to describe everyday life. And if you look at the chart in the book, it tells you that there's all that process of step 1, collecting data, trying to figure out an equation that works with that data, and then after you come up with an equation, you want to test it with the data that you have to make sure that you came up with a good equation. And then you might have to change it and refine it, and then after you're done getting a correct equation, then you can predict for the future. So this question does ask us to predict. We are dealing with step 6 of the mathematical model for question number 5. And whenever I read an equation, what I want to do is figure out what the question is in math terms. So the question here is asking us, predict the number of digital photos printed at home. And that basically says find a value of a variable. Am I finding t or am I finding h? Let's look. It says predict the number of digital photos. The number of digital photos is represented by h. So this question is telling us find h. Well, in order to find h, we must know the value of the other variable. So let's look for that. So it says not only do we want us to find h, but we want to find it in 2008. And 2008, we look at this. T is the number of years after 2000. So what value of t am I using? T is not equal to 2008. 2008 happens to be 8 years after 2000, and so that's what we're going to use. We're going to say t is 8 years after 2000. And so there we have basically the math question we're asking is find h when t is equal to 8. So you're going to write the equation. And then you're going to replace that t with 8. And then solve. And then it's not good enough just to say 5.9. We want to go back and look at that equation. Reading about H is the number of digital photos printed at home in billions. This is the units I need to use. So I need to say that that is 5.9 billion photos printed at home. Remember, whenever we want to use a word problem or we're trying to predict something that happens in the future, we want to take the equation, the statement as it's written, and we want to translate that into math. So what I did was I identified the question. I identified that it's asking me to look for H, find H, and then it also would be when t is equal to 8. Looking at all the data in this paragraph to help me set up a valid equation that fits the model. We're switching gears a little bit to get to our third objective, which is compound interest. And we want to make sure that we know all the variables in questions that deal with compound interest. And so we have A, which would be the amount after the interest has been applied. And then we have P, which is the principal amount, which is the amount that you're starting with. And then we have R, which is the rate, which you want to always express as a decimal. So they might say 7%, then you'd write that as 0.07. And then T, which is how much time has passed. And you want the rate and the time to match. So usually the rate is compounded annually, or even if it's not compounded annually, the rate is given as an annual percentage. So the time, we want it to be in years, typically. And so we're going to do question number 6 using these as our variables. And I have question number 6 written here. Suppose that $1,000 is invested at 6% compounded annually. How much is in the account at the end of the third year? So we're going to write our equation. A is equal to P times 1 plus R to the T power. Now this is 1 plus our rate. So that's 100% is what we start off with. That's why it says as a 1. And then we're going to replace all those values. Let's see if we can identify those values in our equation. So let's look first for the principal amount. Where would I find that? We're investing $1,000. So that's going to be my P. All right, and it's invested at 6%. So my rate would be 6%. Let's label it as our R. And then it says how much is in the account at the end of the third year. That would be our time. So let's label it as our T. So now that I have my P, my R, and my T labeled, then I can go ahead and plug that into this equation. I'm going to write A is equal to 1,000 times 1 plus 0.06 to the third power. And let's just simplify that once. That's 1,000 times 1.06 to the third power. Now, I expect you to use your calculators, so we're going to simplify 1.06 to the third power first because we do exponents before multiplication. So we're going to get A is equal to 1,000 times 1.191016. And then we're going to multiply that by 1,000. And you get 1191.016. Now this is a dollar amount, right? And so when we look at this, we say, how do I present that in a better way? How much would the account be? Well, it would be with a dollar sign, $1,191. And we don't normally deal with numbers beyond the second decimal point, so I'm going to round up to 2 pennies to make sure that I'm putting this in a way that makes sense for money. And so let's double check the question. It says how much is in the account at the end of the third year. We have a dollar amount. That makes sense. Or we could maybe label this much is in the account at the end of the third year. Now question number 6 was compounded annually, and so that equation was slightly less complicated than the one we're going to do for question number 7, which happens to be compounded monthly. Now I told you already that the interest rate is an annual interest rate, and the time should always be measured in the same amount of time, years. So if we're measuring in years, how do I do something where it's compounded monthly? Well, that's an interesting question. What we do is we take one more variable, which is n, and that's going to stand for number of times compounded in 1 year. And that's how we're going to adjust the interest rate and adjust the time to make more sense of this. The equation's slightly different. It starts off the same. A is equal to P times 100%, but we're going to adjust our rate to be divided into so many compounding times, and we're going to multiply how many times we're going to compound per year. And so the n shows up twice in this equation. Now let's go back to our equation and figure out what all our variables are. So our principal amount is 4,000, so we're going to label that as P. Let's write it on the side. P is equal to 4,000. We see that we have an interest rate of 3%, and so that's going to be our interest rate. And so I'm going to label it R, and I'm going to write on this side 0.03. It's compounded monthly. How many months are in a year? Well, we know then that's going to be our n. And so n is going to be 12. And it says how much is at the end of 5 years. So that's going to be our time. And so we label that as t is equal to 5. And so taking all of our variables and plugging them into the equation, this will be what we get. The amount I have is going to be 4,000 times 1 plus 0.03 over 12 times 12, to the power of 12 times 5. And let's simplify that a little bit. We're going to say that's still 4,000 times 1.0025 to the power of 60. Once again, I don't expect you to do this by hand. I expect you to use a calculator. So let's go ahead and use our calculator, see what we get there. And it's a good idea to do one piece at a time on your calculator so you can sort of see the values as they come through, and then there's less error that way. We're going to do 1.0025 to the power of 60, and that gives me 1.1616161782. I'm sure there's more numbers to that. If you have your calculator open, instead of typing this in, I would just let you use that. You're going to multiply that by 4,000 and make sure to be most accurate, don't round your number until the very end. So keep as many digits as possible on that number. Multiply it by 4,000. I get 4,646.467. So I like to write at least one decimal place that I'm not going to use. And then I know it's money, so I'm going to write it as money. I'm going to say $, $4,646, and I'm going to round this up appropriately to 47 cents. Make sure that you always use the correct units. We're going to use the $sign in this question. Make sure you always use the correct amount of significant digits. If you're using your calculator, please don't use 1.16 times 4,000 because you're going to get the wrong answer. You're going to be off by a few pennies or maybe by a few dollars, and that's significant. So you want to use as many digits as possible when you're doing their multiplication. And don't simplify until you get to the very end. All right, thank you. That's section R1, and we're done for the day. Thank you very much. Have a good day.